Welcome! Welcome to the webinar. We're here at Analytical Answers, which is celebrating 25 years of failure analysis and analytical research in the pharmaceutical, foodstuffs, and other allied industries, and interesting applications of scanning electron microscopy to challenging problems across all industries. Today we're going to be hearing from Edward Norton, who is the technical director here at Analytical Answers and has wide experience working with pharmaceuticals, working on contamination issues and on the performance of foodstuffs and pharmaceuticals in a variety of different conditions. As we mentioned a little bit earlier, questions are going to be taken about 45 minutes into this webinar. You can ask your questions, however, at any time using the question or chat feature on your screen. However, we do ask that you keep your questions towards the end or that we will get to them. The main presentation, again, will go for 45 minutes and is being recorded. With that, I'd like to hand over to Edward Norton, who's going to start the demo and the webinars. Welcome, Ed.
Thank you very much. Of course, everyone can see the title here. We're going to be visualizing hydration and dehydration of various materials using wet scanning electron microscopy. And this is actually a very interesting field because it opens up a wide opportunity of experiments you can do in the scanning electron microscope that you just can't do any other way. So, without any further ado, let's move on to our presentation. So I'm just going to give a quick overview of what I'm going to cover today. I'm just going to do a very quick introduction to the basics of scanning electron microscopy for those who may not be familiar. And that's an example on the right of a scanning electron microscope image. And that's actually a comparison of a piece of cotton cloth to a piece of paper towel, and we'll actually see a video about that later. We'll talk about what wet SEM is and what the difference is between it and just standard scanning electron microscopy. We'll talk about some of the things we can use wet SEM for. We'll get a little technical for a couple of slides where we talk about how the wet SEM differs from a normal SEM and what the limitations are along with the benefits. I'll run through several examples showing you some nice videos. I hope everyone loves videos. I know everyone loved it when the teacher used to bring in the AV cart. Realized you could just watch videos for most of the class. And then I'll give a little summary at the end. So here's a basic schematic cross-section of what a standard scanning electron microscope column looks like. What we start with is a source of electrons, and that's a filament. It could be made out of many materials, but it runs in high vacuum, a very low pressure, in order to produce an electron beam. The beam then passes down the center of the column, again in high vacuum, and towards the sample at the bottom. On the way, we have lenses and coils which focus the beam at the surface of the sample and also cause it to scan, which controls the magnification, the field of view that you are going to be looking at. And once the beam hits the sample, it interacts with it to produce secondary and backscattered electrons, which we can use to image, and it also produces characteristic X-rays, which you can use for elemental analysis. Basically, the practical upshot is that you get high resolution, high magnification imaging, and of course, elemental analysis thrown in to boot. Again, this is another example of a scanning electron micrograph of a starch-based food additive, which is another one of our examples from later. And the image, again, would have been created by scanning the beam over this surface, and wherever the beam hits, we get secondary or backscattered electrons, which we use to generate the image shown here. So, what is a wet SEM? Well, first of all, it's also called environmental SEM or ESEM, which is a name some people may be familiar with. Very simply, it's an SEM into which you can introduce gas and water vapor and then precisely control the humidity. And having the precise control is what makes the difference between a very good ESEM or a more run-of-the-mill instrument. Of course, we have the very best. Samples can be brought in wet and kept wet, or they can be brought in dry and made wet. And in both cases, you can observe phase transformations, or you can prevent them by keeping a wet sample wet so that it doesn't dry out and you can image it in its more natural state. Combined with mounting the sample on a cold stage, you can look at fully saturated conditions, or you can bring in frozen samples and keep them frozen during the imaging and the analysis to, again, prevent phase changes where they're undesired. And where you are trying to introduce changes, you can cycle them through reproducibly so you can look at multiple exposure times when exposing a sample to different humidity conditions. So why do we want to use it? Well, there's three main reasons, and I've kind of alluded to them in the previous slide, but the most basic one is charge neutralization. Normally, samples must be conductive when they go into the SEM, or made to be conductive by applying a coating in a vacuum system, which is kind of the standard process. But when you have a SEM that can introduce gas and water vapor, then the gas and water molecules can perform neutralization for you. And that can be advantageous when you have highly structured samples where getting a uniform coating would be difficult. And so the uniformity of the gas and water molecules around the sample actually provide better neutralization. The other thing you can do is prevent dehydration, and again, you can put in wet materials and reduce or control the rate at which they dry out. And again, you can do this very controllably, and one example would be tissue samples where you want to keep them wet to prevent them shrinking or deforming. But foodstuffs and inks are examples of materials where you may want to control the rate at which they dry out so you can see what type of morphological changes occur as they dry out, how they shrink and change their morphology. So the normal thing that we would do is expose samples to water vapor and or liquid water depending on the conditions, and we would record changes in texture and structure as a result of this interaction. Just a side note, you don't always have to involve water. The temperature controlled stage can be used on dry samples, and of course you can just look at deformation of materials as a function of temperature changes over the range that we can obtain. And by doing so, just look at how polymers or organic matter changes as a function of temperature and time on a very micro scale. So, how does the wet SEM differ from a normal scanning electron microscope? Well, this is a blow-up of the end of the column nearest the sample in the sample chamber. And what makes it different is this pumping that's put through the bottom end of the electron column. And by having this extra pumping down here and adding apertures in the center location through which the beam can pass but gas can be siphoned out through the side, you can control the pressure in the gun and maintain the high vacuum which the gun needs, which we talked about when we went over the basics of scanning electron microscopy, and have the higher pressures in the chamber that you need to have these experiments go through and get to the wet conditions on the sample itself. In addition to having that specialized pumping system, you need to have a cold stage. In order to get to truly wet conditions, you typically have to cool the sample below room temperature. And again, you can also go to freezing conditions where it's desired. Of course, you need a water source, and that comes from a bubbler attached to the instrument. And when you're visualizing the samples, you really need to have specialized detectors which operate under the higher pressures that we get to during these experiments. Some of the normal detectors that you're used to using with a scanning electron microscope just don't work at these higher pressures, and so you need to have some different material sensors in order to get them to see under those conditions. So the first consideration refers to the pumping system and the apertures that you install into the end of the column to give you that differential pumping. And so first you have to think about what pressure you need to get to in order to achieve the proper wet conditions, but the choice of aperture leads to a smaller field of view in most cases. So for instance, if you need to go to a maximum pressure of 1,000 pascals or 7.5 torr, then you would have a 1 millimeter field of view for unobstructed field of view. If you go to a lower mag, you get kind of a looking through a porthole look. Similarly, if you need to go up to 3,000 pascals or 22.5 torr, then you install a smaller aperture, and that limits your field of view to 0.5 millimeter or 250x for having no obstruction in the corners of your image. If you only need to go to low pressures, you can still maintain a very wide field of view. And all these numbers I've quoted are for a short working distance of 8.5 millimeters. And the reason for maintaining a short working distance is if you go to long working distance, you lose resolution because of additional gas scattering from the high pressures present in the chamber. So those are some of the considerations you have to think of before you start one of your analyses. So the next two parts of the equipment that I referred to are the cold stage and the water source. This is a picture of our cold stage. It has a temperature range of -25°C to 50°C. It works on a Peltier cooler with a water chiller as a heat pump, and it allows us to very rapidly change the temperature between those extremes. We have a bubbler for deionized water that introduces the water vapor into the chamber, and of course you don't need a lot of it, because even at very high pressures in the wet SEM, there's still very low atmospheric pressures. I'd mentioned the detectors for the wet SEM. And when you're doing standard high vacuum SEM, you have a standard secondary electron detector of the Everhart-Thornley type, and that works wonderfully in high vacuum, and it's what gives you the most surface sensitive imaging, the secondary electrons, whereas a backscatter detector typically gives you more compositionally sensitive information off of a sample, especially in high vacuum, but it does provide some texture information. When you get to these higher pressures in the variable pressure or extended pressure range, when you're looking at charge neutralization or fully wet hydrated imaging, you can see that the backscatter detector still works through the entire range, but the Everhart-Thornley secondary electron detector doesn't work at these higher pressures. So the instrument has several other types of detectors, a variable pressure secondary electron detector and what's called an extended pressure secondary electron detector, which has two components, a ring and a needle. And by choosing the appropriate detector, you can get the most surface information out of the sample when you're trying to do your high resolution imaging. Now, if you're not necessarily going for the highest surface resolution, the backscatter detector does provide a very adequate morphological signal, and it does have the advantage of being a little bit more stable. So when you're shooting videos, which we almost always do when we're recording these experiments, at least all the examples I'll show you today will be some nice videos. The backscatter detector was used almost exclusively because of its stability. So all those things kept in mind is that even at high wet SEM pressures, like I said, 22.5 torr, the pressure is still significantly below atmosphere. So if you have highly porous materials, you might get some gassing, which would be expected when you have that higher pressure gas coming out into the low pressure in the SEM. Because we have to get fully condensed conditions at a fairly low temperature, typically below 10 centigrade, then that can slow down the reaction kinetics if you're trying to watch a chemical reaction occur. So you just have to keep that in mind and keep the temperature constant if reaction kinetics is what you're trying to follow. Because of the gas scattering time of the beam, and also because of the detector types that work at the higher pressures, you typically can't capture video at more than 1 frame per second because you want to get adequate signal to noise. And so that does limit how quickly you can acquire data. You can't get a 30 frames per second video, live video, like you would from your standard video camera. But that's all because you're working at high magnification and you need to get more signal to noise than you can do with think of a standard optical system. But those two things kind of cancel out in that the slower reaction kinetics actually blend well with the slower acquisition time. So they kind of compensate for one another. And the last limitation is that the cold stage actually has a fairly small working area, about 6 millimeters across, and that's because it has a very fast response, so you want a very low thermal mass. But the other issue is that samples themselves can create a temperature lag if they're not thermally conductive. So you would want to have smaller pieces of sample anyway in order to have reasonable thermal conductivity through the material you're trying to image. So having small sample sizes isn't necessarily a limitation in terms of achieving the goal, but it is a limit that you have to think of when you're planning your SEM analysis. And our next consideration is, how do we perform this analysis? We can think of looking at the phase diagram here for water, and the y-axis is the pressure in the chamber, and the x-axis is the temperature of the cold stage. And by selecting combinations of pressure and temperature, we can either work at ice conditions, fully wet conditions, or vapor conditions. And you can choose to cross the transition from water vapor to liquid water in two different directions, basically. You can keep the pressure constant and change the temperature of the cold stage to go from vapor phase to liquid phase, or you can keep the temperature constant and change the pressure to go from a vapor to a liquid phase. And which you choose depends on the types of materials you're imaging. Constant temperature is going to be better for monitoring reaction kinetics because they'll stay the same throughout. But constant pressure is going to be better for video imaging because the detectors stay more stable as a function of pressure. So depending on the materials under observation, it may be more important to choose one or the other. Just a note about the videos that I'll be showing you, starting with our first example, which is coming up next. All the video is recorded in high definition, either 720p or 1080p. It is recorded at around 1 frame per second. You can record faster, like I said, at the expense of signal to noise, but if you want them to look nice and crisp, we go a little bit slower. But we play them back at increased speed because some of these experiments, which take 15 or up to 40 minutes, take a long time to watch, and I'm not going to make you sit through a 40-minute video, but it can be played back at 30 times the speed for more natural viewing, and then you can see all the changes occur in just a minute or two. We can extract high-resolution still frames from specific portions of the video, so you can later review how the sample looked at a specific time, temperature, or pressure. And customers always get the full video, but for this presentation, I'll just select portions. And of course, after the video is recorded, we add things like annotations and elapsed time in order to make it nicer to watch. So here's our first example of a pharmaceutical product. It's a capsule shell. So when you look at this type of medication delivery system, you have the inside components, which can be small granules or a powder. And then the outside, of course, is a dissolvable shell, which again allows the medication to enter the body. And the rate at which the outside dissolves is one of the conditions which affect how quickly the medication will be dissolved by a patient. This here is a SEM image of the surface of that capsule shell when seen in the SEM. In addition to being able to dissolve when you want it to, you also want it to not dissolve when it's just being stored so that it's ready for use, and so it must be relatively stable against the environment to prevent spoilage. So I have videos where we'll compare 3 different formulations, which were variations in the cross-linking and blending of the materials to produce a fast delivery capsule, a slow delivery capsule, a more extended release, and then a mixed blend experimental material. So let's go to our first video. It's going to be of the quick dissolving. It's going to be exposed to 100% humidity. And what we're going to find here is I'm going to play the video. The humidity is going to be shown and the temperature are going to be shown down in the lower right. This is a 500 micron field of view, so a 250x image. And the elapsed time is going to be the large increasing numbers in the lower left. There may be, I'm going to talk over these videos, but there may be a little bit of lag for some people depending on their internet connection. So if my voice is out of sync, I apologize to those of you on such connections, and you can always watch the recording later and get the perfect in sync version. So let's begin. So again, here's the quick dissolving capsule shell, and as it promised, in just a little over a minute exposure to 100% humidity, the entire thing completely dissolves and starts to gas and produce a large amount of bubbles, and then we start to reduce the humidity. And this experiment basically went very, very quickly. We just played back 4.5 minutes and 30 seconds. And so now we're going to watch a video for the slow dissolving, and this actually will be also exposed to 100% humidity, but we'll actually go through multiple cycles here in order to fully dissolve the material, because it's so slow and stable it doesn't actually dissolve after the first exposure. So here we are up to 9 minutes exposure time, even though it's only 10 seconds into the video. We're at 100% humidity and very little has actually started to occur. Now we start to see some droplets on the surface, and you can see that they wet the sample in a very specific pattern because they do not wet it uniformly, and that could be a result of differences in material homogeneity. Or it could be a result of a surface treatment, which makes the water not wet it uniformly. And those types of features can be examined using other methodologies like imaging FTIR. And again, we see that there are patterns that are preserved in the surface of the material after each successive wetting cycle. For this last cycle here, which we're at the 33-minute mark of real time, even though we're only about a minute into this video. And here we go for full solvation, and we're basically seeing the surface of a droplet of water here, and then we start to dry it out, and now the material starts to bend and shrink because it's been fully saturated, although you can see some very interesting microstructure inside the surface here, which gives you some idea about how this material started to break down. I'm going to go back to a slide here where I've actually taken still images from that same video at the 0, 19, 26, and 40-minute marks so that we can compare the structure at each of those points. So here at 0 we have basically no effect, of course. After the first wetting cycle, we saw some of those little islands of material that changed, or controlled rather, how the water was actually able to wet on the surface. After a second wetting cycle, we could see that some of those patterns were reinforced, whereas some others are much fainter than they were the first time, with a little heavier wetting. And then we finally went through the full dissolution or full wetting of the sample for a more extended period of time, and basically completely dissolved away all of those surface features we had observed in the first place. But we did observe some new micro features on the scale of less than 20 microns. And so the last experiment for this sample was the one that was an experimental blend of a fast and a slow. And again, we have 100% humidity exposure that we're going for. And after 2 minutes of real-time exposure, we could see that some of the material started to react just like the first material, the gassy material, that reacted extremely quickly. But most of the sample actually has no change. And so this illustrates that the materials mixed very non-uniformly, because you had large domains of the fast material that was completely unblended with the slow material. So this was not a viable experiment from the goal of trying to create a homogeneous blend of those two materials to get an intermediate style rate. So now I'd like to go into an example of a Foodstuffs project. And this is a texture modifier which can be added to modify the texture of foods to which it is added. And here we have two materials. They both come from the same base stock, but then they're processed in two different ways. One results in a very large flake material, and the other results in a very small flake material. And this is what the starting material looks like. It's got some very large pores in it, and it's got some highly wrinkled surface area, which would add a lot of texture. So now we're going to go to our next video, which is an example of looking at the large flake material. And this is exposure to a lower humidity, only 70%. And this is a 800 micron field of view, so a 150x image. And after 7 minutes of exposure, there is very little difference between the start material and what we see here. And even running it out to a 15-minute exposure doesn't really show much of a change at the 70% humidity level. So then we're going to switch to a higher humidity. And actually, if you look down in the lower right, this is up to a 90%. And almost immediately, there's a much stronger reaction of the material at the 90% exposure. So clearly, we've crossed a threshold where the processing of the material went from a very stable state to a much more reacting state. And actually, if we go for just the full 100% here, where we get the material fully covered in water, again, we see the surface of a droplet of water here with a lot of bubbles in it as the material gases. And this is going to carry on until we dry the sample out. But we can see that we get a very different morphology compared to what we had with the 90% humidity exposure. And so it's interesting that the kinetics or the mechanism of how the material degraded is so different when you compare just a high humidity exposure versus a fully wet exposure. So if we go back to our slides, again, this is just some comparison stills. And if you look at the top two images, the top left we have the large flake at 70% with initial time, and then after 15 minutes at 70%, you can see a noticeable difference between the start and the end image, but you couldn't actually follow that very clearly in the video, because between each second of video there was very little difference going one to the next. But when we compare the stills before and after, you can see that there is a definite swelling to the entire surface of the sample, but it clearly doesn't go through the same change that we see at the 90% humidity, where when we look at the before and after stills, it's a huge difference between the two, although you can still see some vestiges of the original structure in the material. It is basically fully reacted. So now when we look at the small flake material for comparison, this is starts out at 80%. We could see that it has a much stronger reaction. We had to react the large flakes at 90% humidity to get this type of reaction out of it. But the processing applied to the smaller flakes caused them to react sooner. And then here we ramp up the humidity up to 90, then eventually 100%, just to fully react the flakes. And the goal here was to see how they perform differently or behave differently compared to the large flake, so you can understand something about the mechanism change that occurs as a result of the different processing. And this is a higher mag image of the same type of smaller flake. Again, start out at 80% humidity, which we see in the bottom right, and then we go up to eventually 100% humidity after an 8-minute roughly exposure, and really drive the rate much faster. And then we dry it out. If we look at the small flakes with 100% humidity, this here is an experiment where we did multiple cycles of the humidity increased to 100% to fully wet the material. And the interesting feature here was to see how well they glued each other together. So when you start with more discrete flakes and you start to extract materials out of them, you want to see how these are going to knit together to form essentially a larger structure. And you can see that these actually do indeed change their structure significantly, so that they actually almost look like they were initially a larger flake as they get glued together with the material being extracted out of them by the water. And if we go to just some extracted stills here, again, we can look at the difference before and after of the small flakes at the 80%, or we can look at the difference in looking at the still images of the 100% humidity after the full 3 cycles from the video I just showed you. Here we're going to go back to our capsule, but instead of looking at the gel like we did before, we're going to be looking at the internals. These internals also help control the rate of delivery, and here we have a comparison between a capsule that would just contain a powdered material with a very fine grain to larger granules, which are agglomerates and held together with binders in order to further control the rate of delivery of these materials. Now, for both of these, it's interesting. Again, you can see materials being extracted out of them and redeposited on the surrounding stage. But these very large granules, which are on the order of a millimeter, were actually quite challenging. Here's the initial image of one of those large granules, and my field of view here is about a little over a millimeter. And you can see it has a very rough texture with a lot of little nodules. And because of its width and height, it actually took an incredible amount of wetting in order to fully solvate this particle, or not fully solvate, fully saturate. So if we go to that video, we go to 100%, and we're looking at the extended release granules, and this video was sped up very rapidly because of the height of the particle. It took a lot of water on the stage to actually fully engulf this, and you can actually see it slowly creeping up the sides in order to fully cover this particle. And so it's definitely very wet in there at this point in time. You see some gassing, but you can see that this took almost 20 minutes of exposure in order to get to that point. And now we start to dry the particle out, and by increasing the temperature and changing the relative humidity, and then we go through a second phase. We saw that there was a very big difference in appearance between the initial state and the second state. But successive wettings did not seem to cause as significant a difference to the appearance. It seemed to be very slowly changing, but in order to get a very significant change beyond the first cycle, it would take many, many more cycles. And again, that's why this is an extended release formulation, because it's made to be very, very slow. One more cycle, apparently. But again, not much has changed in terms of the appearance of the particle itself after that first wetting. Although it does seem to be becoming a little flexible, because when it dries out each time, you actually see a little bit of shrinkage. I'll actually play that little bit of video again. You can see once it starts to dry out, it has a breathing motion to it as it starts to shrink, as it stops swelling once the water is driven out of it. Because that was such a long experiment, took about an hour to do those multiple cycles, I have some stills here of the particle after each phase. And so again, here's the first cycle of exposure, and comparing that again to the initial state. That's the biggest difference we see. When we look at successive cycles, the change is not that great. We also have the powdered material that we examined. Again, here's a quick release formulation, meaning that the granules are smaller and more readily dissolved because they have a larger surface area. And this is an 80% humidity exposure. And again, we see a lot of gassing when the surface is just becoming wetted and allowed to become mobile. And then we slowly ramp up the humidity to 90 and then eventually higher humidities to get the particles fully wet, but in a more gentle fashion because we ramped it up fairly slowly to see how they behave, and then of course dried them out at the end. When we look at the other quick release formulation particle and we go to a very rapid wetting, then we can see that the way that it dissolves appears a little bit different. We see a lot of extracted material sitting on the mount around it, and we go through multiple iterations of the wetting here in order to just see how the particles differ from each other and also from the larger granules, see how the different conditions affect them. Again, this was about a 14-minute experiment, which we played back in 40 seconds, which seems like a fairly natural playback time. And again, we have before and after stills for each of these samples again, so that we can do comparisons, more detailed comparisons and spot checks during post-review, as opposed to having to watch the videos multiple times. We can take these screenshots in order to get a better look at each one of those stages in its decomposition. We also, that's my last fully worked through example. I do have just one quick video to show you, and it refers to this first example here. So we do have a lot of other applications this could be used for. The first one is textiles, although the list is almost endless. But the reason why it's good for textiles is the complex physical structure is difficult to uniformly coat, so extra charge neutralization that you get from this is especially useful. But if you've applied coatings and treatments to different fabrics or coatings, then you can see how well they were applied by looking at how the individual fibers of a material wet as the water is introduced, and get an idea of how uniform those coatings are, how effective those hydrophobic or hydrophilic coatings are. You can also look at adhesives, sealants, and glues as they cure and dry. You can actually put little pieces of material together with adhesives and then watch the edges of the joints and see how the material behaves. If it's a water-activated adhesive or a sealant, then you can certainly watch the reaction occur. You can get water droplets to form on small components and do micro contact angle measurements. If you have samples where it'd be impractical to do it with a standard contact angle setup. You can watch paints, inks, and other materials dry and see what type of microstructures form. And again, you can look at mechanical changes with only temperature change if you don't want to involve water, or it's not an appropriate variable for the types of materials that you want to look at. Let me go back to my last video, which is of the textile example, before we move on to the conclusions. So this is two videos played back side by side of a cotton cloth and a paper towel, and they're both going to full wet, and you can see the water filling in the gaps between the fibers on each of the materials. And then when we start to dry out, you can actually see again how the materials dry and how their shapes change. You see a lot bigger shape change on the paper towel, for instance, as it dehydrates out, whereas the overall shape of the cotton cloth didn't change that much, but it has a bunch of significant change to the individual fibers as they absorb fluid. So just to go for a very quick summary, it's very useful for looking at the morphology changes and phase changes in different materials as we change the saturation of those materials, and we can look at very high magnifications. I gave only a few examples here, but really it can be applied to many different types of samples. I can't even think of the full list. Just for charge neutralization alone, there's a very large list, but there's so many different types of materials where looking at them in their natural wet state is a benefit over drying them down for a normal SEM, because they lose a lot of their information if you have to go through such an extensive sample prep to dry them out. And of course, we can access a whole range of conditions from dry to 100% humidity, and also a very wide temperature range in combination with the wet or just by itself. Here's just some examples of images that were taken with the cold stage set to very cold. This is some snowflakes, and they're not the prettiest ones in the world because snowflakes are very fragile. But then on the bottom here, if you turn up the water pressure and turn down the temperature of the cold stage, actually you can get ice crystals to form right on the stage itself, and you can grow them and shrink them as you change the conditions. I'd just like to announce our upcoming webinars. February 7th, we're going to be doing some video real-time X-ray microscopy for failure analysis, where we look inside components in order to try and understand why they aren't functioning properly as part of a full failure analysis. Something non-destructive like real-time X-ray is always a very good place to start in any failure analysis. And then on March 17th, we're going to be talking about the art of failure analysis of printed circuit boards and other electronic components. And we'll have our expert Joe Bedard talk about root causes versus red herrings that can result of poor sample prep or poor understanding of what you're observing when you're looking at these findings. Thank you very much for your attention. I do appreciate it. If you have any questions, you can type them in now on the right-hand side of your screen. You can also send them by email to answers@analyticalanswersinc.com. Please just in the subject line put webinar questions, and you can visit us on the web at www.analyticalanswersinc.com. Thank you very much. We'll take your questions. I know some people are really shy, and that's understandable. The first question I have is, could I visualize how a food or drug sample changed under freeze drying? And the answer, of course, is yes. Because we can obtain very low temperatures and can control the humidity, we can actually watch how a freeze-dried sample rehydrates, or we can actually freeze dry a sample by cooling it and dehydrating it. So you can actually reverse the process somewhat in chamber, and so you can cycle back and forth between those if your sample was appropriate for that. Looks like someone else is typing in another one here. Can I image a wet surgical dressing? Anything wet is perfectly fine, and a surgical dressing is certainly going to work well because it's a high texture material, and the charge neutralization will really help cover that. The The field of view, you might wish for a larger field of view, but you could take multiple images in a panorama under the same conditions. So I think that would work out just fine. And if you wanted to see, again, how those materials swell and shrink, if you have additives on them for blood clotting or anything like that, then I think that would also work. We have another question here. It says, can we watch changes in bacteria during dehydration? Yes, of course. Any biological material is perfectly suited to looking at wet SEM. We can load them into the chamber fully wet, actually completely covered in water, so that they're completely in a natural state. And then you can dehydrate them slowly to the point where you can just locate them, because of course you can't see through the droplet of water as we saw in my videos. You only see the surface, and then once you locate the subject that you'd like to watch, you can further dehydrate it and take it down to a dry state. And we have another question here. Looks like, can I watch how a polyurethane glue expands as it sets? I kind of alluded to that when I talked about the adhesives. Yes, you can watch those materials as they change and react with the water vapor or temperature. If it's a heat-sensitive adhesive, then you can certainly watch how those materials behave as they cure or set. Absolutely. This is a very good question. The speed at which the product dehydrates is critical to its shelf life for this particular customer. Can the SEM accurately determine that under different conditions? I think we already saw that some of the samples I showed, we can see very, very accurately when there's even very subtle changes, but depending on the shelf life, it may not be practical to do a full experiment if you have to follow an FDA protocol that goes out to days or weeks. We can simulate rapid acceleration of conditions by using a combination of increased temperature and the water vapor, but if you, and so that would be good for doing product R&D, but it's not a substitute for a full FDA protocol. Sorry, I'm just cycling through some of the other questions here. Have you done any work on hydrophilic coating on medical catheters? Not specifically on catheters, but I did mention that you can look at hydrophilic or hydrophobic coatings on textiles, which I could talk about, but it should work exactly the same on a polymer surface for a medical catheter. So I think that would be perfectly visualized in the wet SEM. So I don't see any problem with that at all. The next question I see is what type of wet SEM am I using? We have a Zeiss Evo, and it works very well. It gives us very fine control over the conditions, and actually it excels at doing the wet SEM with some of the best control over the humidity and temperature out of any of the available instruments. Let's see, getting some good questions here. This is a question about what about in vivo availability, drug availability of rigid dissolvable tablets. You can certainly look at that. Depending on the size of the tablet, you may want to pre-section them just to look at smaller pieces, because as we saw, we do have a limited field of view, and I know most people don't take pills that are just 1/2 millimeter across, but certainly WetSem can look at the reaction of the contents of those tablets and individually at the surfaces to look at how those two react together in order to estimate delivery of those materials. All right, I think that looks like all our questions for now. If anyone thinks of any others, feel free to send them to our email address, or feel free to rewatch this webinar once it goes up on the internet, which you will get a link to once it gets uploaded. And then from there, thank you very much.